Okay, in this video we're going to look at some additional reactions that alcohols do. We've had a few of them before. Remember that in the first half of the class there was an alcohol chapter, but most of those reactions that we saw back then were more or less focused on breaking this bond right here, the carbon-oxygen bond. The reactions we're going to look at now are really focused on breaking the CH bond adjacent to the alcohol, or the one that's on the same carbon as the alcohol, and breaking the OH bond. Okay? All right, so the first one we're going to look at is kind of a mixed, it's a blend of the reactions we've had before and some new ones. Okay, so recall back in when we looked at how to make alkenes, one of the favorite ways to make it was to take an alcohol, treat it with sulfuric acid and heat, and just dehydrate it. Okay? All right. And that's a very good, very general reaction with one exception. Okay? And this is when we have primary alcohols and we try to do this reaction. What you find here is that the reaction really doesn't produce very much alkene at all. In fact, if you take ethanol, sulfuric acid, and heat it, your major product is actually this product right here called diethyl ether. Okay, and water is a byproduct. And this alkene here, ethylene, you really make very little of it. Okay, all right, so what's happening here is that, remember, if you recall alkene stability, ethylene is the least stable of the alkene types. It's completely unsubstituted. All right, so it's not very favorable to form it compared to more substituted alkenes. So this reaction typically produces ethers and not alkenes. All right, so let's look at the mechanism for this reaction. All right, so like before, sulfuric acid is simply going to protonate the alcohol, but because this is if this left, okay, let's just hypothetically look at that. Suppose we just lost water from here, okay? And let's look at the carbocation that we would generate. And this is a primary carbocation, right? And these are not very stable. Okay, so this is very high energy. We're not likely to form this one. Okay, all right. So because we don't make the carbocation, other processes take over. And what happens here is that we do an SN2 reaction like this, okay, with another molecule that hasn't been protonated yet. Okay, this just comes along, does the SN2 reaction, displaces water, and this gives us the protonated ether, and we just lose the extra proton. It kind of just redistributes itself in the media, and we're going to end up with the ether that you see right here. All right, now let's imagine we have a more substituted compound. All right, when we try at this point, the loss of water is actually not so bad, right? Because the carbocation that you make here is secondary or tertiary, and those are comparatively easy to form. All right, the major limitation of this reaction is kind of limited to the formation of symmetrical ethers, okay? Let's imagine we want to make an unsymmetrical ether by taking N-propyl alcohol and ethanol and trying to make ethyl propyl ether. Well, there's no control over who reacts with who. So you're going to get a statistical mixture of dipropyl ether, ethyl propyl ether, and diethyl ether if you do this reaction. So you'll make some of your desired product, but you'll have a kind of a hard separation ahead of you. So it's not a very selective reaction. So one would only use this reaction when you want to make symmetrical ethers. Okay, another reaction that we'll look at, and we're going to look at this in three pieces, is ester formation. And ester is formed from the reaction of a carboxylic acid and an alcohol, and we're going to take up the fine details of ester formation when we talk about carboxylic acids. But this term ester is kind of a more general term, okay? And what it really means here is that we've taken the acidic proton of an acidic compound and we've replaced that acidic proton with an R group. Okay, and the type of ester we have is dependent on the type of acid we have. Okay, so when we have the acidic proton of an acid replaced with an R group, we generate something called technically a carboxylate ester, but this is the most common type, and when we say just ester by itself without saying anything else to describe the ester, that's what it means. Okay. All right, if you take a sulfonic acid, replace the acidic proton with an R group, you get a sulfonate ester. We've already looked briefly at the chemistry of those. A tosylate is an example of a sulfonate ester. If we take phosphoric acid and replace one or more of the hydrogens with an R group, we get a phosphate ester. These are important in DNA and RNA structure. And if we take nitric acid and replace the acidic hydrogen with an R group, we get a nitrate ester. These are important too as explosives, either desired, like for building a highway through a mountain, or undesired for blowing something up. Okay, all right, so here's the basis of why nitrate esters are explosive. This is the compound nitroglycerin. Okay, and it basically has enough oxygens to burn itself. It doesn't need oxygens from the environment. So if you just take it's a kind of a shock stable, unstable compound. So if we just hit a little bit of it with a hammer, we create a pressure wave, and that would induce the compound to convert to carbon dioxide, nitrogen, and water. Okay, these two are gases, so the volume expansion is tremendous, right? As each gas molecule wants to occupy 22.4 liters. This is not balanced. There's a lot more of these. There's at least 3 CO2s and at least 3 nitrogens coming out of this. So this is an incredibly exothermic reaction that results in a tremendous volume expansion, and that's where the explosive nature of nitroglycerin comes from. Okay, all right, so we're going to discuss the fine details about how ester formation works here, but in the carboxylic acid chapter, but we're just going to look at the basic reaction equation here. An ester is formed by just taking a carboxylic acid and an alcohol and some sulfuric acid as a catalyst, and this generates our ester here and water. When you look at a conventional carboxylate ester, just ester in general, we divided it into two parts. This part over here is called the acid part because this part here comes from the acid, and this part here comes from the alcohol. Okay, we'll discuss the mechanism of that in the carboxylic acid chapter. All right, so for now, this is just going to be presented as a reaction equation. Okay, we're going to reinforce it by looking at the reaction also in the carboxylic acid chapter and in the ester chapter as well. All right, so if we took this compound, benzyl alcohol, and this compound, cyclopentane carboxylic acid, we treat it with a little bit of sulfuric acid, we'd expect to generate this ester right here. All right, notice how I've expressed this as an equilibrium arrow, and this kind of makes this reaction sometimes difficult to run. If you really want a high yield of ester and you don't want to worry about the reverse reaction, what you would do is you would prepare it from an acid chloride, a type of compound we've seen before in the Friedel-Crafts acylation back in the aromatic substitution chapter. Okay, so if you take an acid chloride and an alcohol and with a little pyridine present here, you'll also make an ester, and you'll make as this byproduct the hydrochloride or HCl pyridine adduct. So pyridine kind of has a dual role. It actually activates the system, and it sort of sops up the HCl that's formed as part of the balanced equation. All right, so if we took this acid chloride, cyclopropane carbonyl chloride, and this one butenol, we would generate this ester that you see right here. Okay, all right. We've already looked at reduction, how we make alcohols from ketones and aldehydes. Well, we can do the reverse reaction as well. We can convert alcohols back into ketones and aldehydes through an oxidation reaction. All right. So if you look at this reaction here of a primary alcohol making an aldehyde, note that the net result is that we lose 2 hydrogens. Technically, these are the 2 hydrogens that we lose. Okay. And remember, loss of H2 is technically an oxidation. This makes the aldehyde. The aldehyde is kind of a complex situation because an aldehyde can also do an oxidation itself up to a carboxylic acid. So this is a more oxidized state here. Recognize that we're just adding this oxygen right here. And when we add just an oxygen all by itself, of course, that's an oxidation. Okay, if we take a secondary alcohol, okay, we can do a very similar reaction. We can remove these 2 hydrogens right here in an oxidation reaction, and this makes a ketone. So a secondary alcohol gives a ketone, and the further oxidation of a ketone is a little bit more difficult because you'd have to break a CC bond. Okay, and a tertiary alcohol, we don't have any hydrogen here, no hydrogen on this carbon. So our oxidation is going to be very difficult for this type of system. So we're going to see that primary alcohols oxidize to either aldehydes or carboxylic acids, depending on the oxidant that you choose, and secondary alcohols oxidize to ketones. All right, oxidations, there are many choices, okay? Historically, chromium-6 has served as the most common oxidizing agent for organic chemistry. However, if you do any sort of proper literature search for how many reagents are known that will turn an alcohol into an aldehyde or a ketone, you'll find probably more than 2,000 compounds known to do that. All right, so let's just look at some equations here. We'll briefly look at the mechanism too. All right, so this is chromic acid right here. And we can also use chromium trioxide or sodium dichromate. All of these have the common feature that they are chromium-6. Okay. All right. Okay, so if you oxidize a primary alcohol with these reagents here, what you're going to find here is that you do not get the aldehyde, but you get the carboxylic acid as your product. Okay. Let's look at the mechanism here. The mechanism involves taking chromic acid and just making the chromate ester here. All right. We then do a reaction here. Sorry. Let's see. Let me erase those arrows. They kind of suck. Okay. All right. So Yeah, so we do is we basically oxidize or reduce the chromium this way, and in the process oxidize the alcohol to get the aldehyde. Okay. The complexity here exists because of we're working in an aqueous environment. We'll talk about this reaction in the ketone chapter, but ketones in the presence of water undergo this equilibrium formation of a hydrate. Okay, and what you notice here is that a hydrate is also an alcohol. So this is an alcohol, and we can remove a couple of hydrogens out of here too, and this secondary oxidation process is very difficult to stop, and we end up with a carboxylic acid. All right, so what we have to do is we have to eliminate the water if we want to stop at the aldehyde stage. Okay, so this is a compound here called pyridinium chlorochromate. Okay. I'll just draw it out one time. Kind of a mouthful, right? And we're just going to abbreviate this in all reaction equations with these three letters, PCC. Okay, this is done in the absence of water. When there's no water present, you don't make a hydrate, and your product is the aldehyde, and the reaction does not stop here. Okay? All right, with a ketone, it doesn't matter which form of chromium-6 you use. You'll always get this, with a secondary alcohol, you always get a ketone because the further oxidation is difficult and requires a different type of reagent that we'll look at in the ketone chapter. Okay, so any form of chromium-6, whether it be PCC or chromic acid or sodium dichromate, any of those will convert a secondary alcohol into a ketone. All right, so one of the reasons that people want to design new alternatives here is because chromium-6 is kind of a hazardous compound. You might remember that it's the subject of the movie Aaron Brockovich, where some electrical utility company poisoned the town's water supply by improperly disposing of their chromium waste. Okay, so chromium-6 is toxic, but remember, chromium comes in various oxidation states. This is a picture I took in the right from a local health food store. What you see is they have a total chromium section, so it's thought to be an important trace nutrient in glucose metabolism. So yeah, there's a whole 2 shelves devoted to chromium, as you see here. Further down, there's magnesium and some greens or something. All right. Okay, so it's kind of so chromium-6 is something that people want to eliminate. There are many alternatives. I'm just going to discuss one. This is called the Spurn oxidation. This is a completely organic, or this uses only organic reagents. All right, so in this reaction here, we're going to take as our oxidizing agents a mixture of oxalyl chloride, dimethyl sulfoxide, and triethylamine. Okay, in the balanced equation here, you generate a couple of gaseous byproducts, carbon monoxide, carbon dioxide, kind of a stinky compound, dimethyl sulfide, and the chlorines and the hydrogens go away as the ammonium salt derived from triethylamine. All right, and this is done under anhydrous conditions, so you don't have to worry about oxidation of your aldehyde further to a carboxylic acid. We're just going to look at the mechanism. I don't think it is usually asked on an exam, but let's just look at it anyway. DMSO is our net oxidant, okay? Okay, this is what's actually gets reduced as a result of the reaction. All right, so sulfoxide, if drawn this way, you can see that the oxygen's nucleophilic. Oops, I do not have enough lone pairs there, sorry. It's going to do the nucleophilic addition. Okay, this is going to now kick out chlorine to produce this. This is going to do this funny process here, making carbon monoxide and carbon dioxide and chloride ion to generate this compound here, which is this is the species that actually reacts with the alcohol to do the oxidation. And here's the oxidation process. Nucleophilic addition to the alcohol to sulfur produces this. Triethylamine removes this extra hydrogen. This makes one of our triethylamine triethylammonium ions, and then another triethylamine comes, displaces the sulfur leaving group, and the process converts the CO single bond into a CO double bond, and this finishes the reaction. All right? Okay, all right, there are a lot of different ways to turn an alcohol into a carbonyl compound. We're just going to focus on either the chromium-6 based methods or the Spurn oxidation in this class. So let's just complete a few equations here. PCC on this compound has an alkene and an alcohol. It's just going to turn the alcohol into the aldehyde. It won't oxidize further. Chromic acid, using this alcohol here, it's not going to touch the alkyne, but it is going to produce a carboxylic acid as the ultimate product, and you get that product that you see here. And this third equation here, this is PCC, and this is a secondary alcohol, but remember, secondary alcohols react with all forms of chromium 6, and this is going to generate the ketone that you see here. Recognize that there is this extra carbon here, so this is a ketone and not an ester. Okay, an ester would have the oxygen directly attached to the C double bond O carbon. In this last one, we have the Spurn oxidation. Again, this reaction only occurs at the alcohol, and this produces this aldehyde right here. Okay, a common problem people make when completing these reaction equations is losing or gaining carbons. Always try to remember that the number of carbons should stay the same when you do any of these oxidation reactions that you see here. Okay, these are multi-step transformations here, but these are common things that people have to accomplish in organic chemistry. How do you add an alkyl group to the same carbon that's attached to an OH group? All right, you can't do that in one step. All right, but we have to take advantage of the fact that an alcohol is very easily turned into a C double bond O. Okay, and a C double bond O, remember, we can add Grignards and organolithiums to the C double bond O to make alcohol. So that's what we're going to take advantage of. All right, so this is a new carbon right here. We're going to have some sort of either methyl Grignard or methyl lithium to complete this reaction. But it can't be done in one step. All right, so what we have to first do is oxidize the alcohol to the aldehyde with pyridinium chlorochromate. Since it's primary alcohol, we have to use PCC. Okay, and then we would treat it with methyl Grignard, followed by acid to finish the reaction, or just turn the OMG into the OH, and that would produce that product right there. All right, here's another one. Recognize that here we have two carbons between the phenyl ring and the OH group. Here we have three. Okay, we're still going to have to use this Grignard chemistry but we're going to use it differently here. Okay, we're going to think about this as actually being from formaldehyde. Okay. Okay, so we know that we can very easily make this bond right there, that CC bond, by adding a Grignard. Okay, we cannot make a Grignard from an alcohol, but we know that we can turn an alcohol into a halogen very easily. So the way you would do this reaction is to turn the OH group into the corresponding bromide. This doesn't have any other functional groups now, so this should react with magnesium ether quite easily to make the Grignard reagent, and then we would just treat this with formaldehyde and then quench the reaction with H3O+, and that would give us that product right there. In this final slide here is where I'm going to stop the video, but we're going to just go through this roadmap problem, and this has got a lot of review reactions, but it's good to not forget these. All right. In the first one, we're doing an aromatic substitution reaction. We're treating methylphenyl ether with bromine and FeBr3. If you remember that reaction, it replaces one of the hydrogens on the ring with a bromine, and this is the product that we're going to get there. Let's say we forgot whether OMe is an orthoparadirector or a metadirector. We have a clue here. Okay, and this is the beauty of roadmap problems. So if we forgot that, we would probably suspect we're probably going to have to put this in the para position right there, right? Okay, so there's a clue in the structure of the final product that we have to put it in the para position, but OMe is a strongly electron donating group that's an orthoparadirector. All right. In the next equation, we're making a Grignard reagent from our aryl halide. That's our Grignard reagent right there. We're treating that with an aldehyde followed by H3O+. That's just going to add the Grignard to the aldehyde carbon, and we're going to, since it's an aldehyde, we're going to get a secondary alcohol out of this, and that's our product. Okay, we're going to treat this with chromic acid. Secondary alcohol gives a ketone. All right, and a ketone is going to react with methyl Grignard here, and this is going to put a methyl group right here. All right, and that's going to give us the alcohol, tertiary alcohol. And now we're going to do probably, again, what I call the most memorable reaction from the first half of the class, dehydrating an alcohol. That's the one that people can remember 20 years after they had organic chemistry. All right. Okay, so sulfuric acid is just going to eliminate water, and according to Saitsev's rule, we should produce the product that you see there. All right, so this is where this video is going to stop, and we'll finish the chapter in one more video.